Right, hello chaps. So let's go over how to do the work energy theorem conservation of energy question set. 5 questions. There's multiple parts to each question, but the idea is to try and help you go through the steps with those, little sections, subsections of it. So don't let them trip you up. First one, you got this fellow riding a motorbike. The dude in the motorbike have a mass of 240 kilograms. I think I actually changed this on yours. So that should be 240 kilograms. Motorbike starts from mass producing a net force of 600 newtons over a distance of 20 meters. What will be the motorbike's final velocity? So he's opening up the throttle, applying a force, he's accelerating. He does that over 20 meters. What's his final velocity? So how much work does a motorbike do? Easy. Work equals force times distance. Run the numbers, 600 times 20, you're done. If all that work is converted to kinetic energy, how much kinetic energy will the motorbike have after it travels 20 meters? It's going to be the exact same. I'm not trying to trip you up, but a lot of people get tripped up here. The kinetic energy is going to equal the work is going to equal whatever answer you had here, because all of that work got converted to kinetic energy. What will be the velocity of the motorbike after it travels 20 meters? Well, here's the deal. Now you know what the kinetic energy is, because that is whatever this answer is here. But that is going to equal 1/2. Let me see if that makes it easier. 1/2 mv squared. That's what kinetic energy is. So you're just going to have to do your magic there. Rearrange for v squared. So I would multiply by 2 to both sides. I would divide by m both sides. Divide by m. And then you're going to want to square root both sides. Square root. And I think you're going to end up with v is equal to the square root of 2 times the kinetic energy over mass. You run the numbers for that, you should be good to go. So that's question 1. Question 2. Geraldine driving a car 15 meters a second, notice a cat, her in a car, mass, frictional force of 5,400. Same question, except it's backwards. She has kinetic energy, she brakes. How much work needs to, how far is she going to skid to stop, right? So, first of all, what's the kinetic energy of the car? That's easy. Kinetic energy is equal to 1/2 mass times velocity squared. You know what the mass is. This is a mass, 1200. You know what the velocity is. It's 15. So you run the numbers, you'll get an answer. How much work needs to be done to stop the car? All that kinetic energy got turned into work, so it's going to be the exact same answer. Whatever number you got here is going to be the exact same thing down here. Calculate the distance the frictional force applies a brake, force of the brakes are applied over. Work is equal to force times distance. We know that. You know how much work is done because it's the exact same as the kinetic energy, which is the work right there, is equal to force times distance. So all you're going to do is rearrange, divide by f, divide by f. Sorry, my coffee machine is making funny noises in the background. Work is distance is work divided by force, and you'll get your answer. Question 3. It's the exact same. However, she's going 30 meters a second, not 15 meters a second. So you can do the same thing again. The only thing is 30 meters a second, not 15 meters a second. So the interesting thing is she's doubled her speed. So what I want you to do is see how much that has changed the kinetic energy, how much that's changed the work, how much that changes the braking distance. If she doubles her speed, you should find that it actually quadruples her braking distance, right? Okay. Conservation of energy. Alright, so this one, you got a dude jumps off a 7-meter high diving board into a swimming pool below, mass of 80 kilograms. What velocity does she hit the water with? Alright, so first thing you're going to need to do is draw an LOL diagram before she jumps. Let's be honest with ourselves. There is no rotation, there's no spring. There's no rotation, there's no spring. So it's all about kinetic and gravitation. Person right at the top, this person here is not moving, so there's no kinetic. They are lifted off the water 7 meters up, so there's gravitation. Right here, they're hitting the water, so there's no gravitation, but there is going to be kinetic, right? So you can do that. Calculate the potential energy before she jumps. Easy peasy. Potential energy is equal to mass times gravity times height. We know the mass. Mass is 80. We know gravity is equal to 10 because we're lazy. 10 meters per second squared. We know height is 7. So MGH, height is obviously h. MGH is just going to be what, 80 times 10 times 7. How much kinetic energy does she have when she hits the water? Here's the thing. We said over here, I mean, if we do this, right here, there's no kinetic, but there is gravitation. Over here, there's kinetic but no gravitation. All of that gravitational energy gets turned to kinetic. So whatever answer you have here, basically the gravitational energy gets turned into the kinetic energy. So it's going to be the exact same number. So then, knowing that, what is the velocity when she hits the water? You're going to do the exact same thing. Kinetic energy is equal to 1/2 mv squared. You are going to rearrange this for velocity, which we did up here. When you rearrange it for velocity, you end up with square root of 2k over m. And you're going to run your numbers. Velocity is equal to square root of 2 times kinetic energy over the mass. Run all your numbers, and you should get that. Now, if Henry has a mass of 160 kilograms, big old Henry decides to jump the pool after what velocity will he hit the water with? Hence, does it matter in this case? Look, at the end of the day, we kind of discussed this in class yesterday, but whatever gravitational energy you have here got turned into kinetic energy here. Gravitational energy got turned into kinetic energy. Mass times gravity times height got turned into 1/2 mass times velocity squared. It does not matter how big you are. Your velocity is still going to be the same, which I think in this case is this velocity is equal to square root of 2gh. But my point is there's no mass in here. It doesn't matter if you're a 5 kilogram person, a 50, 160, 300 kilogram, the velocity is still going to be the same. All right, last question. Bridget's going down a 10-meter high ski slope. She skis down the slope, friction free until she reaches level ground at the bottom. Okay, there's a whole bunch of friction stuff. Okay, so first of all, draw an LOL diagram. I don't see why this would be any different to the one above, honestly, because at the end of the day, why have we got a little circle there? Doesn't matter. At the end of the day, she's not moving at the top. There's no rotation. There's no spring. I don't know why I did a different order here. So it's just gravitation. At the bottom, she is not lifted. She's not rotated. No spring. So it's all kinetic. And then here, up as she stops, there's nothing, no energy, which means it's left as work. But let's deal with that in a second. Calculate Bridget's potential and kinetic energy at the top. You know how to do this. Potential energy is mass times gravity times height. You know the height, you know her mass. Mass is 64, the height is equal to 10. You know gravity is 10 meters per second squared. So you can do that. What's the kinetic energy at the top? Kinetic is equal to 0, right? There is none. Okay, what's Bridget's potential and kinetic energy at the bottom? Kinetic energy, she has, potential is going to be 0. But here's the thing, all right, maybe this is worded a little bit funny. What's her kinetic energy? You don't know her velocity, but basically her kinetic energy at the bottom is going to equal the potential energy at the top. So you don't need to show me any calculations, just show me that potential energy at the top equals the kinetic energy. Because again, all of this gravitational energy got turned into kinetic energy, right? So it's going to be the exact same number, the exact same value. How much energy is lost as work done by friction by the time she stops? Well, guess what? All of this energy is lost as friction. It's going to be the exact same answer again. Right? Because the initial potential energy got turned into kinetic energy, then was lost as friction. So you don't have to show any work to show me that you understand that concept. Calculate the force of friction at the bottom of this ski slope. Alright, we're back to forces. Force of friction is equal to mu times the normal force. At the end of the day, if this person is on skis, that's a ski. And they've got the little sticks, because those, I don't know what the sticks are for. Hitting people, maybe, I don't know. But anyway, if you do a free body diagram, you got the person's right here. You got the force of gravity is acting down, which is equal to mass times gravity. Normal force is going to be exactly the same. It's going to also equal mass times gravity, just acting up instead. So the force of friction is going to equal mu times mass times gravity. Mu, we said, was 0.2. Let me put it up here. Mu is equal to 0.2. Her mass was equal to 64 kilograms. Gravity, you know, is equal to 10 meters per second squared. So you can run that. That'll give you the force of friction. And then finally, what distance is the force of friction done over? Well, again, work is a force over a distance, right? And this is the force of friction times the distance she slides. So let's have a think. The distance is going to be the work divided by the force of friction. The work is this. It's that one. And the force of friction is that number there. So you plug them in, you'll get an answer. Now, all the answers are at the bottom. So do check your answers, make sure you get the right answer. And that is all I have to say about that. So I hope that was helpful. I hope someone watched it. But yeah, okay. So I'm going to upload this video now. I hope you're doing alright. I'll see you guys tomorrow. And yes. Okay, good stuff. Take it easy, chaps. Adios. Hasta luego.